the Earth. Okay. Okay. So let's start. Okay. So good afternoon to everyone again. During the next 3 hours, so maybe something less, I'll show you some data about the Earth climate history. It is a very complicated history, very complex history. And I think that we can have 2 breaks of about 10, 15 minutes every 45 minutes, more or less. It's fine. And following this plan, I think that we will have enough time at the end of the presentation for questions. However, please feel free to make your questions also during the presentation, okay, if you have any. Moreover, in this first slide, you can see my email address. So also after these lessons, if you have questions or if you want more materials about this topic, please contact me, okay? No problem. You can find anyway in the virtual website some additional materials in addition to the PowerPoint presentation, okay? So just a few words to introduce myself. I'm Veronica Rossi. I'm a geologist at the Department of Biological, Geological, and Environmental Sciences at the University of Bologna. And I'm interested in the responses of depositional environments and ecosystems to climate change, to climate oscillations through time, to relative sea level change, and to the human impact at different time scales and with different amplitudes, okay? And I study especially the last few hundreds of thousands of years of responses of paleoenvironments to climate change. So a very short time interval. If you think about the age of the Earth, you know the estimated age of our planet is about 4.5 billion of years. So a lot, okay. However, I'm not a paleoclimatologist, but for my research, I need to have a good knowledge about this complex history of Earth climate. And I think that the history of Earth's climate is a very hot topic. It's of interest for many scientists, but also for the whole society and also for the policymakers that have to take decisions about the state of health of our planet, of ourselves, of our society. And also this topic is particularly interesting because of the issue of the global warming, of the global change. And maybe you may wonder how, in which way, a better knowledge of past climate condition of our planet could help us for a better understanding of what is going on now for our climate system and which will be the future for our climate system and so for all of us. For example.
Sorry, teacher. Can you share the presentation, please?
Oh, sorry. You're right. Ok, condividi schermo. Okay. I forgot it. Sorry, now you can see the presentation.
Yes, thanks.
Okay, thanks. Sorry, forgot it. Okay, but I was still at the first slide indeed. So just look to this graph, to this figure, where you can find the variable value of climate condition, especially the alternation of hot and cold period over a wide time interval of our planet. You see at the horizontal scale, you have the more or less more than 500 of millions of years of climate change for our planet. So we can, during the first part of this presentation, this lesson, I try to show you in which way this kind of knowledge can help us for a better understanding of the state, the present day state and the future state of Earth of our climate system, for example, the polar ice caps. Okay, so I try to show you in which way the past could be the savior for the future in this specific issue for what concerns the climate change, the climate condition of our planet. So the first slides will deal with the introduction to the paleoclimate studies. I show you the main concept and why we should know past climate conditions also for a better understanding of what is going on now and what will be in the future. Then I show you a very nice, although draft, so it's a draft, it's a preliminary results of the project concerning the reconstruction of the average surface temperature change of our planet over the last 500 of millions of years. The also so-called the Earth fever line. And we will see that, and I'll tell you now, maybe it's better, why we usually refer to this time interval. You know why? What's happened around 500 of millions of years ago? It's the time, more or less, of the so-called Cambrian explosion. So it's the explosion on our planet of the life, oxygen-based life. Okay, so it's a very important point in the timeline of our planet. It's the start of the life as we know, okay, oxygen-based life. Then I show you more data about the methodological approach used by paleoclimatologists to obtain quantitative and robust reconstruction of past climate condition, natural, obviously, natural condition of our planet. So I try to answer to the question where in the geological record and how we can obtain such kind of data. Finally, I hope we will have enough time. I want to show you specifically the oscillation in terms of paleoclimate conditions, so mainly temperature and precipitation, occurring over the last 2.5 million of years. So the most recent period of time of our planet, that is called Quaternary by geologists. Now you know that we are living into the Quaternary period, okay? And this period, it is quite short if we think about the Cambrian explosion of life, oxygen-based life, is very, very important for paleoclimatological studies because it's full of climate, natural climate oscillations at different time scales and with different amplitudes. So it's a very nice period of time to produce good paleoclimate data. Okay. First, we have to take a look to a very important principle for natural sciences. That is the uniformitarianism principle, stated by Charles Lyell and James Hutton at the beginning of the 19th centuries. And these principles say, the present is the key to the past. That means that if you want to understand the geological record, what's happened in the past, you have to look to the present day geological processes and products, because we assume that these geological processes remain unchanged through time. This means, as a consequence, that we think that biological, chemical, physical laws remain unchanged through time. However, we can go beyond this principle and, in certain sense, look at the other side of the coin and think that the past is full of information about the past, more or less back in time, of the events occurred on our planet. So it's a sort of laboratory, of library, the geological record of a lot of data, also concerning climate conditions. So as if we read this sentence, a knowledge of the past can strongly improve our understanding of the present world, especially in the environmental sciences. We can expand back in time our record, instrumental record about temperature, for example, okay, or precipitation, or in general, climate conditions. So the geological records, that means rocks, sediments, deposits in more general sense, but also ice, for example, can be seen as a natural laboratory containing a lot of information and data useful to improve what? Our comprehension of the natural climate dynamics of our planet. And against these natural dynamics, we can plot then what is going on now, also under the forcing of the human impact on the environment, on the planet. And in this way, we can improve a lot climate models and projections. Because here, okay, there's a good, nice photo of a very nice, maybe very nice outcropping of limestones in Sicily. And all these limestones are very, very layered. You see here, layer by layer, and contains each layer a lot of information about past climate condition during the deposition, the formation of this succession of limestones. Okay, this is the first approach of a paleoclimate study in our slide, but we'll see this better few slides far. Okay, why we have to expand our paleoclimate records back in time using the geological record? Because the instrumental data are very nice, very precise, but we have at maximum a more or less continuous record, for example, of temperature, global average surface temperature, for the last 170 years, okay, at maximum. Here is the present day and the mid of the 19th century. Since the mid of the 19th century, we have good data, instrumental data about, for example, temperatures, average temperatures, okay? And you can see what, for example, comparing these two graphs, this is the graph of the temperature anomaly. Okay, just a moment, sorry. I don't look to this graph now. Just look to the graph concerning the value of the temperature since about the mid of the 19th century. You can see very clear a steep increase in global average temperature since about more or less the second half of the last century. This is called the Great Acceleration in terms of temperature of our planet. This is a big part, the main part of the issue of the global warming, okay? And all these data are instrumental data collected and combined against this chronological timescale by the IPCC, that is the International Panel on Climate Change, that you know, I think, okay? And you can see this kind of graph into the summary, for example, for the policymakers. That means that it's like a technical records, okay? And another interesting graph reported by the IPCC report in a few years ago is another global average value. That is the sea level change in this case. And you can see that from the beginning of the last century up to now, we have an increase of the relative sea level global rise, but specifically, we have since about the second half of the last century, a great acceleration in the relative sea level rise. So again, we have two important climate in a general sense parameters that show that we are living into a great acceleration period of both temperature and relative sea level rising trend. Okay, but it's not enough because we have to contextualize better this data into a more long time period, okay? Considering the age of our planet. And to do that, to do this, we have to search into the geological record for paleoclimate data. Here, a nice figure representing the different periods of time of our planet. It doesn't matter all these names, just a name given by geologists, okay? But as you can find in the rocks, sedimentary rocks, deposits, a lot of fossils, okay, that give you information about the evolution of life on our planet. Similarly, we can search for indicators, proxies inside the same, for example, rocks or sedimentary record to extract quantitative paleoclimate data. For example, paleo-temperature data to extend back in time this reconstruction, okay? And maybe see if the great acceleration that we are living now is something out of scale of the recent past history of the Earth climate. It's okay, it's clear, this point, it's a very important point, okay? So we need to expand the paleoclimate record, and we can search into the geological record using some specific methodology and specific indicators. So starting from the beginnings, just a definition. What is paleoclimatology? It's the scientific discipline that studies the Earth climate, and it's dynamic through time and space. We would like to better understand the natural time and mode of variability of the climate system of our planet, because the climate of our planet is full of, is extremely dynamic, is full of variation, change at a different amplitudes and at a different resolution scales. Here, you can see the draft, the preliminary results of a very big project involving a lot of scientists interested into the paleoclimate of our planet. And this project and this draft, these preliminary results, even if are approximated, maybe contain some errors, because this graph needs to be, this reconstruction needed to be improved through time. it's very important. It's very interesting because it shows you the global average temperature of our planet through time since about 500 million years up to now, today. And you can see how much is variable. Here you can see also the quantitative reconstruction of this data, so you can see the temperature in Celsius degrees. Okay, so paleoclimatology is very important because provide evidences for the baseline level of natural variability of Earth climate systems, and at the same time can provide information about the responses of ecosystem and the position environment to such variability. So if you can do a good work, you can extract from the same geological record for a certain period of time, climate variability, and the response, the consequences on the environments of such variability. And this is very important. Both of these information are very important for future climate and to better understand future climate and environmental trends. But even if all these points are so nice, we must confess that it's very hard work. It's very difficult to obtain robust, quantitative, good paleoclimate information from the past record, from the geological records, because we have a lot of problems. Okay. For these reasons, this reconstruction is very nice, but it's just preliminary results. Okay. But I want to show you this graph because it's very clear, and show you, for example, that our planet naturally can work in two modalities from a climate point of view. Our planet can work in a greenhouse or an ice house modality. That means, what does it mean? It means that if you are in a greenhouse period, our planet is without polar caps, ice caps, because the temperature, the global average surface temperature are too high to allow the development of polar ice caps. On the other side, our planet can also live or work in a world with high polar caps, and then live in a so-called ice house period. And you can see very clear in this graph that there is no, that the climate fluctuation occur from greenhouse to ice house period, but also at a higher resolution scale of observation. You can see that also within the greenhouse period or the ice house period, you have other kind of oscillation of climate variabilities. So it's very complex. So we can say one take-home message is variability is the normality for the climate system of our planet. This variability can occur at different time scales and amplitudes. The greenhouse world occurred maybe for a longer period of time over the last 500 million of years. That this period is also called by geologists Phanerozoic Eon, but it's not important, the name, okay? And we live in an ice world. Ice house world, obviously we have ice polar caps, okay? Polar ice caps, sorry. Just to give you an idea of some of the main events, global events of our planet occurred over this period of time. You can see that, for example, the so-called Cambrian Explosion, so the diversification of life, oxygen-based life, occurred during a very high temperature period, for example. Okay, orange color corresponds to greenhouse period. Polar ice caps formed and persisted for a long time, as far as we know, only around 350 millions of years ago. Reptiles, the predation of reptiles occurring during, again, a greenhouse period around the beginning, around the beginning of Mesozoic. So around 250 million of years ago, mammals, again, during a greenhouse period, around 60 millions of years ago. And we can see here what is going on now about this great acceleration of temperature. Okay, this is very clear from instrumental record, okay? So this is a very nice representation and give you the main concept about the natural variability of the climate system of our planet, but again, is a draft because a global paleo-temperature curve is a challenging task that required a lot of data, paleoclimate data all over the world, and it's very complicated to put together all this wide data set, but also it's a challenging scope because we have to integrate this data set against a robust chronological framework, and dating rocks is always a problem. Okay, we have a lot of methods to date rocks, but all these methods include some errors, some problems, and one important take-home message, I think, that is that you can have a lot of good quantitative paleoclimate data, but if you cannot put them against a robust chronological framework, they are useless. You cannot work with them, okay? So time is always very important for paleoclimate reconstruction. So I think that we can move now into a little bit into detail into the methodology used by paleoclimatologists to reconstruct these paleo temperatures or paleo precipitation or other parameters. So where we should search a good archive of paleoclimate information in the geological record and how we should study it. Again, a definition that I think that could be useful. What is a paleoclimate archive? Paleoclimate archive is a geological or biological material, so natural material, okay, that can preserve inside itself evidence, clues, proof of past change in climate. So can contain the so-called paleoclimate indicators or proxies. It's the same thing, okay? So the archives is the material containing paleoclimate indicators. And the paleoclimate archive can be rocks, deposits, so unlithified sediments, corals, tree rings, speleothems, ice, and so on, okay? Here, another nice picture about a very thick succession of outcropping deep sea deposits, fine grain deposits, outcropping at Monte San Nicola near Gela in Sicily. These deposits formed few millions of years ago under a very thick water column, okay? And we can now observe them because, as not cropping, okay, succession, because of the tectonic forces occurred in this place due to the Apennine chain. Okay, yes?
There are some properties of a certain material that can identify that it is able to preserve information more than other materials.
Yes. In this case, deep sea, the sediments are very good archives because they are continuous record, okay, and include a lot of fossils that are very nice paleoclimate indicators. And for example, in alluvial succession, you cannot have fluvial succession, you cannot have so much continuity into the sedimentation, and no fossils, or very few. So few paleoclimate indicators. I don't know if I answered to your question. Okay. Indeed, deep sea deposits, for these two main reasons, continuous record, guarantee continuous record, and are full of fossils, represent one of the main paleoclimate archives for our paleoclimatology studies. In a certain sense, if you look to this photo, you can see here these layers, okay? So deep sea marine deposits are formed step by step, time by time, by the accumulation of sediments at the ocean sea bottoms, okay? And all these layers can contain paleoclimate indicators. And if we can extract layer by layer through paleoclimate indicators information, quantitative information about paleotemperatures, okay? And if we can date each layer, we can obtain a nice reconstruction of the paleotemperature for the period of time of the deposition of these deposits. Okay, this is another important point that I don't think that is so easy for you, that you are not geologists, so maybe it's something different. Is that yes, it's a different view to observe the nature. Okay, it's okay at this point. It's like to read a stack of book, page by page. Okay, something similar. However, obviously, the development of mountains change like Apennines, give us the opportunity to observe outcropping deep sea deposits. But why we should not go? But it's more, yes, but for which reason we should not go to drill the ocean bottoms and then recover the geological record of sediments, of deep sea marine sediments, where we are still now forming? Okay, so over the last decades, there are a lot of projects, international program or project, like for example, the International Ocean Discovery Program, IODP program, that go into different deep sea, into different oceans, make a lot of drill, of course, and then study all these cores, layers by layers, to extract paleoclimate indicators. Okay, here you can see, okay, the vessels used for the International Ocean Discovery Program. You can see here fresh core, so a cylinder of sediments of the sea bottom. And here you can see an image of the laboratory on board these vessels, where these cores were opened and analyzed and sampled, sometimes centimeter by centimeter. A lot of work that involves a lot of scientists with different expertise, because you need the sedimentologist, you need the paleontologist, you need the geochemist, the chemicians, maybe it's okay, who study geochemistry, isotopes, make the age depth model, so the chronological framework of your sediments, and so on. If you are interested, you can go on the website of the IODP, or also you can check on the YouTube for nice videos about what does it mean to go into the ocean around the world and make a drill, okay, at the sea bottom. Here you can see all of these points corresponds to a core campaign. So we have performed a lot of cores around the oceans of our planet. A lot of data. However, we can also use other kind of natural materials as paleoclimate laboratory archives, or library if you prefer. For example, the coral reef that are still now forming at low latitudes and are composed by biogenic carbonates, because polyps that live in colony form the skeleton using elements from the surrounding water, and then construct the reef. And you can make a drill inside this reef again. And this drill the core can be analyzed again, layer by layer. Okay, and you can extract paleoclimate indicators also from the carbonate skeleton of this reef. We will see soon after which kind of paleoclimate indicator we can use in the different paleoclimate archives. Okay. But also, for example, we can extract paleoclimate indicators, so data from tree rings, and so on, from lacustrine sediments, from speleothems, and from ice cores. So in this case, we go on the polar ice caps, we make a drill, and we extract a cylinder of ice layer in this case, because each season's snowfall has slightly different properties than the last. So these differences create annual layers also in the ice of our polar ice cap. And then we can use this layered structure to count the age of the ice from the top down into the bottom, layer by layer, year by year, and we can extract from each layer specific paleoclimate indicators. It's not so easy, okay? It's very complicated. Firstly, it's very complicated to make an expedition in such kind of environments, polar ice cap, Antarctica especially. It's very complicated, and to do good drill core, we need a very high technology and a lot of money, obviously. Okay. And it's also very complicated to extract information from ice layers. But it's very, very nice paleoclimate archives. If you want to, you can go take a look to the World Data Service for Paleoclimatology, and you can see now, for example, from this screenshot, that each of these points corresponds to a paleoclimate archives with associated paleoclimate indicators and studies all around the world. So you have a paleoclimate data from the deep sea cores, okay, in the ocean. You have paleoclimate data from the ice cores on the ice caps, North and South Pole, okay. You have a lot of data on land, thanks to, for example, speleothems in caves, but also lacustrine sediments, okay, and tree rings and other paleoclimate archives. And if you go on this website, you can select each of these points, and you can see which kind of paleoclimate studies have been done over there. Here, I try to make a sort of summary of the main, but it's just a summary, okay, of the main archives that we can use for paleoclimate studies and corresponding main proxies or paleoclimate indicators that you can find and use inside that archive. For example, to the marine sediments, this is a photo of a marine core, a deep sea core. You can obtain paleoclimate information layer by layer, analyzing the chemical composition of your deposits, the stable isotopes. We will see soon after what does it mean. Okay. The size of the particles composing your deposits, but also obviously fossils as pollens and spores, but also microfauna, meiofauna, malacofauna, that means mollusks. Okay. So a lot of proxies that you can use if you are studying marine sediments, deep sea marine sediments. That means hundreds or thousands of meters of water column, okay? But also you can use the lacustrine sediments on land with something similar proxies, okay? Speleothems in the cave, and usually in this case, we have stable isotopes as good paleoclimate indicators, and ice cores, where you can find very peculiar paleoclimate proxies. Apart stable isotopes, you can find dust and gas concentration of the past atmosphere above the polar ice cap during the formation of each ice layer. This is something that is quite incredible, no? You can find, you can see bubbles of the past atmosphere during the formation that's occurring during the formation of that layer of ice. So a sample of past atmosphere at high latitudes, obviously. We will see a little bit more in detail proxies in marine sediments, deep sea cores, and ice cores. So if, in a certain sense, at the end member of the big hydrological cycle of our planet. So masses of water and polar ice caps. And we will talk about mainly, for what concerns proxies, of stable isotopes, oxygen stable isotopes, and gas concentration in the ice cores. just a few minutes and then we will have a break, okay? Before the break, I just want to show you, to show you the main, maybe one of the main proxy that you can use on ice cores. Because paleoclimate proxies can be of two main categories, direct or indirect. Direct means that you can directly extract information about the climate parameter. For example, the atmospheric bubble, the air bubbles entrapped into your ice layers are represent a direct paleoclimate proxy because you have a sample of past atmosphere, okay, in terms of composition, okay? Otherwise, there are a lot of paleoclimate proxies like fossils, stable isotopes, values that need to be calibrated in order to obtain a paleoclimate parameters, for example, a value of the paleo temperature. And so they are considered as indirect proxies. So a lot of work we have to do to extract from indirect proxies a quantitative information, for example, about temperature value, okay? This is the last image that I want to show you before the break. Here you can see very easily inside a piece of an ice core, these air bubbles. Okay, it represents a sample again of past atmosphere. And you can extract these bubbles and analyze the composition, for example, in terms of the CO2 concentration of past atmospheres over the polar caps through time. Okay, I think that we can have a break, 10, 15 minutes, fine, okay. I hope that until now, the main concepts are quite clear, okay, and then we can go on. If you have questions, please let me know, okay. Thank you. No, Okay. So let's start with the second part of our lesson. Okay. So we can have two kinds of paleoclimate proxies, direct as the atmospheric gases trapped in the layers of the ice cores, or indirect. So you need a calibration to obtain your paleoclimate data. And an example of indirect proxies are stable isotopes values and fossils. Here, if you are interested in this, the project of the drilling project on the polar ice cap, you can look to this video on YouTube. And here you have a map of the Antarctica, where you can see with these red dots, the main drilling point until now, where we have obtained very nice long ice cores from which we obtained very interesting paleoclimate data. And here you can see, for example, the reconstruction of the concentration in CO2, carbon dioxide level, layers by layers, obtained layers by layers from the ice cores from the Vostok core site in Antarctica. And you can see here these fluctuating values of CO2 concentration back in time to more than 400,000 of years. Okay, the complete record reached around 650,000 years of values of CO2 concentration in the atmosphere above the Antarctica. And you can see very clear, not only this very oscillating value, but also that after the mid of the last century, we are in a world with a very high concentration of CO2, something that seems to be out of scale of all the natural, although fluctuating, all the natural concentration of CO2 in the atmosphere, passed back to 650,000 years. The great acceleration, again, in this case, for what concerns the concentration of CO2. Here, if you want, you can take a look to a video, okay, about what Antarctic ice cores tell us about climate change. But I think that we have not enough time, so I'll leave it on the slides. So if you want, you can take a look, okay? It's a very, very clear video. But we want to go more back in time for what concerns data from ice cores. So there is going on a very big and international project named Beyond Epica, where the aim of this project is to retrieve a continuous ice core back to the bedrock in Antarctica, covering the climate history also for what concerns the CO2 concentration of the last 1.5 million of years. So we want to know more. We want to expand more our paleoclimate record. It's very complicated, you know, to select the right core size, go there, make a drill, a long and continuous drill, and then take the ice cores, open them, sample layers by layers these cores, and extract all this kind of information. Very hard and long teamwork, okay? Again, if you want, you can look to another video about this kind of teamwork. Okay, but from the ice core, here you can see a cylinder of ice before it was open, okay, in two slices. From this kind of paleoclimate archive, you can obtain also, and you can also analyze indirect proxies or indicators, especially stable isotope values for what concerns the ice core. What does it mean? So you know what is an isotope, okay? It's just a different form of the same element. This means specifically that different isotopes of the same elements contain a different number of neutrons, so have a different atomic mass. This means, as a consequence, that different isotopes of the same element have a different physical behavior, but the same, more or less, chemical behavior. And this different behavior, physical behavior, make possible to transform, calibrate value of our oxygen isotopes extracted layer by layer from our ice core into paleo temperature values. Paleo temperatures of what? Of the atmosphere above the cap during the formation of that layer. Okay? And if you can date your layer step by step, you can obtain a long paleo temperature curve. Specifically for the ice core, usually were analyzed stable isotopes of oxygen and hydrogen. Okay, so that is, we have water, so okay. We look to especially to the oxygen isotopes. So this value that you can find in a lot of paleoclimate studies, that is delta oxygen 18. Delta oxygen 18 is the product of this formula. It's quite easy, okay? It's not very complicated. It's the ratio between the value of the ratio of the oxygen isotope 18 and the oxygen isotope 16 from your layer sample, less the value of a standard mean ocean water. So this is your reference value. Okay, and then you again rationalize, you can say, this kind of differences with the same standard value. And then you put a per mil because these values are very, very small. This means that layer by layer, so time by time back in the past, you can obtain value of this parameter that is a geochemical parameter. So you open your ice core, identify your layer, count your layer to obtain a date, an age, take a sample, send the sample to the laboratory, and they give to you this parameter, okay? Because this is the standard value, we know, and this is the value of the ratio between the heavier oxygen isotopes with respect to the lighter oxygen isotope in your sample. So you can have delta, this value that is a delta oxygen 18, that is positive or could be negative. It depends on what. You have this value that is positive if the sample is enriched in the heavier isotope, obviously, okay? This is a ratio. On the other side, when this value is negative, this means that your sample, your ice layers formed at a specific time that you know, is enriched in the lighter isotope. And you can calibrate, even if it's not so easy, this variation through time, layer by layer of this geochemical parameter into paleotemperature values with an associated errors, obviously, okay? So you can obtain something like that, like this graph. Look to the green line here. So the bottom part of this figure. You can see here the reconstruction, the paleotemperature of the atmosphere above the ice cap over the last 800,000 of years. You can see here, this is the mean value, okay? Each of these values is associated with an error, okay? An error bar that here is not shown, okay? You can see that you have a lot of oscillation in temperature since about this time, over this relative short time period of time. And you can see that you have a lot of period for here, when the temperature, the temperature of the atmosphere over the Antarctica was higher than today. We mean today the mid of the last century, okay? And we see again that, for example, around, and specifically, sorry, we see that around 130,000 of years ago, BP, we had a temperature of few grades, two grades, 2 degrees more with respect to the temperature of the mid of the last century. But in between these two high temperature value, okay, we have a long period of very cold, low temperature. This period is called the last glacial period, the Ice Age, okay? Here's the same graph with a different representation, but it's the same take-home message. Okay, you can obtain the same take-home message from this reconstruction. Okay, so over the last for example, 400,000 of years, there was at least 4 periods, interglacial period, warm period, warmer than today, okay? If we consider today the mid of the last century, okay? Because we want to investigate the natural time and mode of variability of our climate system. It's fine. Okay, see?
It's a convention to use the 90 and 50
yes.
as a year of
yes, because of the fact that in this case, in these studies, we wanted to analyze the natural, more or less natural trend of our climate system, of the temperature, because we know that after the mid of the last century, we enter into a heavy human impact climate system with the great acceleration. Okay, this is conventional mode. Okay, way to plot this data. Okay, but we can use, if you remember the table, showed to you a few slides before, we can use the same geochemical proxy, delta oxygen 18, also to extract paleoclimate and specifically paleotemperature values from the ocean sediments. In which way? Using the fossil content of such deep sea deposits. Specifically, we usually use foraminifera that are unicellular organisms, very, very small sized, in the size of the fine sand. So at the naked eye, you cannot see them. you need a microscope, okay? And these organisms are marine, live on the bottom and inside the water masses of the ocean, and construct air shells, carbonate shells, with very different ornamentation and morphologies, sorry. Using what? Using the elements occurring in the water masses around. Because these shells, very small shells, are carbonate, are made in calcium carbonate. So you find what? The oxygen. So you can analyze these shells, these very tiny shells, to obtain delta oxygen 18 values. Okay, first step. You can use the calcite shells of foraminifera to extract delta oxygen 18 values. But we have to know that you can find within your deep sea succession deposits, layer by layer, centimeter by centimeter, a lot of these shells, because they are small size. This is why they are so useful for this kind of analysis, because you just need a very, very few amount of deep sea sediments to extract enough number of foraminifera shells to obtain robust delta oxygen 18 values. In these slides, I try to summarize the main step to extract this kind of information from your deep sea core, for example. Okay, here we have a long deep sea core. You can imagine that you analyze this core and take a sample centimeter by centimeter, layer by layer, sediment sample, okay? You can extract at the microscope from each of these samples the amount necessary to obtain valid, robust delta oxygen 18 values from foraminifera shells. So you make a picking from your samples of hundreds of foraminifera shells. Send them to the laboratory. The laboratory give you for each of your sample, for each layer, a value of delta oxygen 18. You can calibrate it into a Palo temperature value, and you have then to transform your core depth of your sample, centimeter by centimeter, into time using the dating methods. Okay, you can obtain a curve again against time of delta oxygen 18 values, then of Paleo temperature values. It's fine, it's okay, it's quite clear. The procedure to obtain this kind of information from a deep sea succession. So you can obtain Paleo temperature values from the same time interval of the past, from the ice core and from the deep sea sediments, using the same proxy, delta oxygen 18, but from different paleoclimate archives. It's fine. However, for what concern foraminifera, so this kind of materials, this kind of indicators, paleoclimate proxy, inside the value of delta oxygen 18, there are a lot of information, not only temperatures, but also other information about the so-called eostatic, glacial eostatic signal. that means if you are into an interglacial or a glacial conditions. But we will see this a little bit more in detail, a few slides after. In this slide, I just want to show you that you can obtain a more robust reconstruction of paleo temperature, the paleo temperatures back in time, for example, over the last 400,000 years, using the same proxy, delta oxygen 18, from different archives. Okay, you can see that these values of paleo temperature from marine cores using foraminifera shells and from ice core using the ice of the layers are almost the same. Okay, so this means that these data are good. Okay, and you can see again a lot of this oscillation of temperatures. Okay, I think that we have time just to look a little bit more in detail about the foraminifera delta oxygen 18. That is a complex biogeochemical paleoclimate proxy. Complex, why? Because the value of delta oxygen 18 inside your shells of foraminifera depends on two main parameters. One is the temperature of the water around the foraminifera community, okay? So the ocean temperature. Because in this case, you obtain paleo temperature of the water masses, okay? But at the same time, this value is also forced or controlled by another parameter. That is the value of delta oxygen 18 of the seawater. Because they obtain the oxygen from the seawater surrounding them. So it's obvious that this parameter also determine the value of the delta oxygen 18 that you calculate from your shells. And this value, the delta oxygen 18 of the seawater, depend on the ice volume on Earth. What does it mean? It means that if you have more ice, so your polar ice caps increase their volume, you have an increased value of delta oxygen 18 of both water, seawater, and then shells, obviously, okay? But, and obviously on the other side, if you have ice polar decay, you have a decrease in delta oxygen 18 value of the seawater and then in your shell. Likely, the temperature work in the same direction on the value of delta oxygen 18 in the shells. Because if you have a colder temperature, you have an increase of delta oxygen 18 of your shells. And if you have more ice, it's obvious that you have a colder temperature. You are in a glacial period when the global temperature are lower than today and the ice cap increase their volume. On the contrary, if you are in an interglacial period with high temperature, like the one where we live now, okay, you have also a decay of your polar ice sheet. Okay. This slide just to show you that all these calculations are very complex, okay? And you have to take into consideration a lot of complication, a lot of feedbacks, a lot of processes, okay? So the take-home message is this one. That oxygen 18 records from the shells of foraminifera that you pick from layer by layer from your deep sea core sessions provide the quantitative data of the combined measure of the combined effect of change in ice volume and in temperature of ocean water. So if the delta oxygen 18 value in your forams, shells of foraminifera is positive, this means that you are in a glacial period. The sample that you have collected was formed during a glacial period. On the other side, if the delta oxygen T value from your foraminifera is negative, the sedimentary layers from which you obtain this value of delta oxygen 18 of foraminifera was formed during an interglacial period, like the present one, or maybe more warm. Okay. Why? Because the isotopic composition of the seawater is influenced by long-term hydrological, it's wrong here, okay. Hydrological dynamics due to the ice expansion and decay on Earth. I try to explain this concept with this figure. Okay, just look to this scheme. You can see in a very simple way, okay, simplified way, the ice cap at the polar, the pole, and the ocean. Okay, the two main components of the hydrological cycle of our planet. If we are into a glacial period, so low temperature and ice growth, you have this kind of condition in terms of delta oxygen 18 in the ocean water. You have ocean water depleted in the lighter oxygen isotope. Why? Because the lighter oxygen isotope is, because there is a preferential evaporation of the lighter oxygen isotope. So the precipitations that derive from the evaporation of the ocean masses are enriched in oxygen, in the lighter oxygen isotope. And these precipitation are entrapped into the ice cap during the glacial period, because the polar ice cap grow. So there is an ice enriched in the lighter oxygen isotope, and as a consequence, you have a less positive, well, high delta oxygen 18 values in your ocean masses and then in your foraminifera shells. By contrast, in an interglacial period, you have a return of your enriched lighter isotope, oxygen isotope, into the water masses, because we are in an interglacial period, and then the ice cap decay. I don't know if this point is more or less clear. Okay. The main point is, I think, that during the glacial period, the precipitation, snow at the polar, okay, are enriched in the lighter oxygen and came back to the ocean masses because they are entrapped into the ice of an ice cap that is growing up. Okay. This means this is why if you have, sorry, no, this is why if you have high delta oxygen-18 values, you are from your foraminiferous shells, you are in a glacial period, because a lot of oxygen isotope, lighter oxygen isotope, remain entrapped into the glacier, into the ice cap, and cannot come back into the ocean. It's more complicated than this, but it's the main. I think that this could be useful just to have an idea of why high delta oxygen-18 values in the foraminiferous shells corresponds to glacial period. Okay. Okay. So we can look here now to another type of paleoclimate proxies, indirect paleoclimate proxies that's more easy. It is more easy. It's fossils. Why is it more easy? Because it's more, I think, intuitive. Look to this representation. Look to this figure here. In blue, with blue color, is highlighted the area where now, at present, live a specific species of bivalve that is known with the name of Arctica islandica. So this bivalve can live only at relatively low temperature of the water masses. Indeed, these species live at high latitudes. On the other side, there are other species of mollusk. In this case, this is a gastropods with the name of Persistis thrombus bubonius. Very complex name, but it's not important name. That now, at present, live offshore the coastline of the Senegal. So these species need high temperature to live. This is the present-day distribution, special distribution of these two different species of mollusk that can fossilize because they have shells, carbonate shells. So we can find fossils of these both species in our sediments, marine sediments. So I just make you this question, very easy. If we make a drill in the Mediterranean Sea, extract the core, analyze the fossil content of the specific layer of my core, of our core, and we find here, for example, Arctica islandica, what does it mean? That during the formation of that layers, the temperature of the water masses in the Mediterranean Sea were cool enough to allow the colonization of Arctica islandica. This means that you are in a glacial period. It's fine, it's okay. Indeed, Arctica islandica is one of the species called as cold indicators or glacial host in the Mediterranean Sea. On the other side, if you find in your core in a different layers with a different time of formation, with a different age, Persistis thrombus bubonius, It means that during the formation of that layer, you have a temperature of the water masses high enough to allow the colonization of this kind of species, warm species. Okay, so you can use the ecology of present day species to obtain information, qualitative, not quantitative, but qualitative information of paleotemperature of the water masses of the past, for example. Okay, quite easy, I think, this kind of methodology. Indeed, Persistis thrombus, not bubonius, sorry, I was wrong, latus, is quite common into the sediment, marine sediments in the Mediterranean Sea, dated around 130,000 years BP and 110,000 years BP. It corresponds, this time interval, to the last interglacial period. Okay, so higher temperature, high scale decay. Just to make it. Here, this peak in temperature, okay, corresponds to, or here, corresponds to the last interglacial and corresponds to the time when Persistis thrombus latus enter through Gibraltar and straight into the Mediterranean Sea because of the higher temperatures. Okay, and we find them as fossils in our sediments. Similarly, we can use not only fauna fossils, but also plant fossils to obtain similar indication about paleoclimate condition from our sediments, deposits, okay? Indeed, there are some pollen grains or macro remains, seeds, for example, or specific plants that can give you information, if you find them into your deposits, about the paleoclimate condition during the deposition of your deposit. Why? Because I try to make this more intuitive. Okay, why? How? We can use pollen assemblage as paleoclimate indicators to track the alternation of glacial and versus interglacial periods within our sediments, for example. Also marine sediments, you can find pollen, because pollens can make a very long journey, okay, from land into the basin, the ocean basin, flying essentially by the wind. How? For example, think about the present day condition. So we always think about the present day condition and apply the uniformitarianism principle to obtain information from the past. You see? Think about the present distribution of the main vegetation patterns. At present, we are in interglacial period, obviously. We have different vegetation depending at the latitudes. At our latitudes, mid-latitudes, we have a lot of trees, mainly oak, mixed oak forest, like this, more or less, okay? But at the same time now, if we move to higher latitudes, we have tundra with steppe herbs. So we have a lot of herbs, but very few trees, mainly conifers or other kind of trees that can survive with very low temperatures. So if we think about this, if we find an almost oak mixed oak forest better. A pollen assemblage that corresponds to whole oak, mixed oak forest within our sediments of a specific age, we know that that sediments formed under interglacial conditions. By contrast, if we found a pollen assemblage that is interpretable as tundra with steppe herbs vegetation, we are in a glacial condition. Okay, it's the same principle with Persististrongus latus versus Arctica Islandica, but in this case, we look to a very specific type of fossils, microfossils that are pollens, okay? Because each plant produces specific pollen. So you can more or less interpret each pollen in terms of a specific trees or herbs, for example, okay? Okay. The last part of our lesson is focused on the last 2.5 million of years, the so-called Quaternary Period, that I say to you at the beginning of this lesson that it's a very important period of time for paleoclimatologists because it's full of climate oscillations. And also is obviously the period of the appearance of humans on our planet. Here, there is again a paleotemperature curve, but covering only the last 60 millions of years. You can see here the time scale along the horizontal scale. But be careful, because in this graph, in this figure, the authors, Bark and colleague, change the scale to highlight some specific data. So here you have a scale in terms of million of years. In this second part of your figure, you have a scale in terms of thousands of years. So this is a focus on the last more or less 400,000 of years, okay? So you look in more detail into this portion of the time, okay? The most recent portion of your chronological scale. And then here you have the time scale that is measured in terms of years common era. So this is the mid of the last century, and here you have a projection for the future, okay? Of what? Of temperatures. Again, global surface temperatures, but in terms, in this case, of delta. So the differences between your paleoclimate reconstruction and the value of the temperature measured around the mid of the 19th century. So this is the zero, your reference scale for what concerns the temperatures. And you can see that until around 3 million of years, so from 60 millions of years up to 3 millions of years, the mean, the average temperature value of our planet was higher than the temperature measured at the mid of the 19th century. Okay, and specifically around 50 million of years ago, we have our planet experienced a period of very high temperatures. This is also called the thermal maximum period of our planet. But you can also observe that during this time, this interval of time with higher temperature with respect the mid of the 19th century, but also since 3 million of years toward the present day, we have a lot of high resolution oscillation of these temperatures value. Okay, so very oscillating again, temperature values. And you can see here, this part of the graph, your interglacial, glacial, interglacial, glacial, interglacial, glacial periods. Okay, that we look before, that we see before looking to the net oxygen 18 value from the ice cores. Remember? So one take-home message looking to this figure is that on a general point of view, since the 60 millions of years ago, we have a decreasing trend of the temperature of our Earth. But this temperature is very oscillating, and the last more or less 10, 11,000 years BP seems to be more stable in terms of temperatures. You can see that, okay, from this figure. Maybe it's not by chance that during that period, agriculture and civilization developed. Okay. Another important thing is the occurrence during this period time of interglacial and glacial period, and the last interglacial period, the one that is also documented by the occurrence of persistent thrombus lapus in the marine sediments of the Mediterranean basin. Here, with this very low temperature, about 5 degrees less with respect our zero of reference, corresponds to the last glacial period. Better, last glacial maximum. Okay, so the moment of the last glacial period with the lowest temperatures on average. This slide, then we will have a break. Okay, I just want to remember you that when we think about global surface average temperature, we have to think always about the variation in relative sea levels. Why? Because if we are in a glacial period, we have low temperatures and growth of ice caps. This means that the ocean level lowered. And during the last glacial maximum period, dated around 20 kilo years, 20,000 years BP, this is more or less the southern margin of the ice sheet for what concerns the our hemisphere. Okay, so a great part of the North America, Canada, but also Northern Europe and Asian were covered by ice, and the sea level was lower than today, about 120 meters lower than today. And someone tried to reconstruct the Paleo coastline of the Mediterranean basin during the last glacial period. It's not easy, it's very complicated, but from a general point of view, we can see that, for example, here in gray, of course, we have the Paleo coastline during the last glacial period. You can see that, for example, all this portion of the North Adriatic Sea was exposed, was subaerial environment, crossed by Po River and Apenninic rivers. So the Po Delta that now is here, just 20 or 18,000 years BP was located here, south of Ancona. Okay. At the same time, the Tuscan, for example, coastline was here, and some island of the archipelago of Tuscany were connected to the land, because a big part of the platform, the continental platform, was exposed. And all these reconstructions are based on geological data, so are robust reconstruction. Okay. So we know that here we had an alluvial plain, just a few tens of thousands of years BP, due to the lowering of the sea level, connected to the increase of the ice caps, linked to lower temperatures. Okay. Okay, I think that we can have a break. Last one. Okay. Okay. Back to presentation mode. Okay. Well, so now we know that the Quaternary period, and especially the late Quaternary period, is full of oscillations in terms of temperature, so full of alternating interglacial and glacial periods. The last interglacial period is dated around 130, 110 kiloyears, 1,000 of years BP. And after that, there is a long period of time of decreasing low temperature, and then ice cap growth. And the acme of our last glacial period is dated around 20,000 years BP and is known as the last glacial maximum. And during that time, we had a very big drop of the eustatic, of the overall sea level. After that, after the last glacial maximum, we have a rising trend in temperature because we enter into the present day interglacial period, our period of life. And since about 10, 11,000 years BP, we have a sort of relatively stable temperature value. And this period is known with the name of Holocene. So we are living into the Holocene epoch. But if we look in detail to this figure, we can see that indeed also the Holocene period, the Holocene time interval, is full of oscillations in terms of temperature. Sorry. But these oscillations are higher in frequency and lower in amplitude with respect to the previous ones. Okay, so it's just a matter of scale of observation indeed. The Holocene period is not so stable. Indeed, high resolution stable isotope data oxygen 18 from Greenland, in this case, ice core, document very clearly the occurrence of minor oscillation in temperature, also during the Holocene period, the Holocene time interval. And especially thanks to this kind of high resolution paleoclimate studies using both ice cores and marine deposits, marine cores, we can say that the last 10, 11,000 of years are full of millennial scale climate variability. These climate events are small in amplitude, and one of the most important is known as the 8,200 events, 8.2 climate events of the Holocene period. In this case, Morilli and colleague try to map the anomalies, the climate anomalies related to this important Holocene climate event. And you can see here that for what concerns Palo temperature during this Holocene event, we have a colder condition, but not so high in amplitude as for what concern, for example, the last glacial maximum. Okay, at maximum, at the acme, we can find Palo temperatures during this 8.2 kilo-year event, lower than 1.2 degree with respect the present day temperature. So less strong, but widely distributed climate events also during the Holocene epoch. Another important features of this event is that it is also accompanied by change in precipitation rates. But as you can see here from this map, during this event, we have different kind of precipitation conditions or change depending where we are. So at the same time, we can have a climate change toward drier condition in Mexico, for example, okay, or in part of the Southern America, or in Eastern in Asia, in the Asian land. But at the same time, for the same event, we have wetter condition, for example, in the Northern Europe. So this means that especially this high frequency climate oscillation, very recent in time, because belong to the Holocene period, the Holocene epoch, are very complex in terms of especially precipitation, changing precipitation. And is more difficult to map which kind of change can be related to this kind of high frequency Holocene climate events. That means that less expected change are potentially more dangerous, because we are not sure which kind of change in precipitation rates, for example, will occur in the future with similar event. That is in general a cold event, cool event, but in terms of precipitation is very complex, depending where we are. Just remember you that each of these points corresponds obviously to a paleoclimate archive studied with specific paleoclimate proxy that give you such kind of quantitative information in terms of both temperature and precipitation. If we look in very detail to the last 2,000 of years, so we look to historical periods, so historical times, since Roman times up to now, more or less, we can see again, thanks to the same proxy delta oxygen 18 from the Greenland ice core, that we have again a lot of short-term, low amplitude climate events. That are, for example, the Roman period, warm, usually known as a warmer period than today, the medieval warm period, and the Little Ice Age. That is very famous, I think, it's quite well known. And you can see here that there is a sort again of alternation of warmer and cooler period. Each of these events cover few centuries, okay, and the oscillations in terms of temperature is quite small, but is anyway, but can anyway impact on our environments. For example, during the Little Ice Age that began around the beginning of the 14th century, so more or less 500 years ago, the Venice Lagoon was freezed, just for example, okay? And you can see here quite easily looking to this painting, okay, of the time that represents the time, the aspects of the freezing of the Venice Lagoon. And for what concern this kind of historical climate events, could be very useful also integrate paleoclimate proxies from the geological archives with historical documentation, for example, because you are into time, the period of time where you can also have this kind of data. So the last part of our lesson is related to which are the causes of this kind of dynamics of the Earth climate system. So I think that now you know that it's quite it's quite clear that the Earth's climate system is extremely variable by nature, okay? It's naturally variable. But why? It's not easy to answer to this question, obviously, but here I would like just to show you three main external forcing parameters that determine the variability at different time scales of the climate system of our planet. These external forcing factors are change in plate tectonics. Think about the emission in the atmosphere of high amount of green gases, for example, CO2, methane, or other gases deriving from big volcanic explosions, for example, that are related to plate tectonics. Okay. Another important parameter, forcing factor, is obviously our main source of energy and heat. It is the sun. And you know that the sun activity is very variable over time. Think about the sunspot, okay? But I want to give you just a few more information about another forcing factor, that is change in Earth orbit, the so-called Milankovitch theory of climate change, climate oscillations. This change in Earth orbit represents essentially change in the geometrical relationship between our planet and our star, the sun. And this change in Earth-Sun geometry determine over time change in the amount and type of distribution at different latitudes of the heat, okay, of the energy from the sun. This is why, for example, we have seasons, okay? And the main parameters, geometric parameters, astronomical parameters that determine this kind of, determine quaternary climate oscillations, so the alternation of glacial and interglacial periods, are three: eccentricity, obliquity, and precession. I don't want to go into detail about this, but if you want, you can find a very deductive video about this theory on YouTube. It's very, very clear, okay? And I just want to, again, highlight the fact that Milankovitch theory demonstrates that change in orbital parameters, eccentricity, obliquity, and precession, can induce change in the seasonal and latitudinal distribution of solar insolation. So can determine the alternation of glacial and interglacial periods. Okay. This theory is based on astronomical calculation, but obtain a good proof from geological record. We have to better understand some things, but this theory is very good, okay? And what does it mean, each of these parameters? Very easily, eccentricity is the represents how much the orbit of the Earth, the revolution orbit of the Earth around the sun is more or less circular, okay? Obliquity, and this value change through time, following more or less a periodicity of about 100,000 of years. Obliquity is the angle that the axis of rotation of our planet forms with the perpendicular to the plane of the ecliptic, the plane of the revolution of the Earth around the sun, okay? And this value can change through times. So can be more inclined or less inclined, the axis of our planet. And the axis of rotation, okay, of our planet. And these parameters see more or less change over period, following a periodicity of about 20 thousands of years. Lastly, is the precession. The precession is related to a sort of, to the fact that the Earth is like a spin, okay? So the axis of rotation move during time, following a sort of rotational of the circles, okay, in the space. And complete this rotation over about 41,000 of years. So it's very complicated, because if you have a planet that move around the sun, changing the form, the shape of the orbit, okay, more or less circular. At the same time, our planet is inclined, and this inclination, this angle of the axis of rotation change through time again. And through time change also the movement, like a spin of our planet. All these parameters considered together can explain the alternation of glacial interglacial periods, or at least could be one of the main forcing factors for this kind of modality. Okay, see, I think that we can go further to future projection. And this is actually the last few slides about this lesson. So for this lesson, so we think we make a journey, we can say this, through the paleo temperature values, so the paleoclimate condition of our planet. Since about the first period in greenhouse modality up to now, okay, looking to the high frequency climate events of the Holocene epoch. However, what about the future? Thanks to IPCC reports and a lot of scientists that studies and try to obtain robust projection of what will be our future in terms of temperature, global temperature, surface temperature, we can see here that there are a lot of scenarios. We have good, best scenario, middle, and worst scenario of increasing global temperature. One point is how much this increasing trend in temperature, so the great acceleration, is human induced. This is a big question, big issue. We are sure that the emission of CO2, of fossil CO2 in the atmosphere, fooled the increase, maybe the natural increase in temperature of the planet, at least, okay? And this is quite easy to see from this figure, from the IPCC report, that since the mid of the last century, we have an increase in temperature. We have an increase that corresponds to an increase in CO2, methane, and other green gases in the atmosphere. And this increasing trend corresponds to an increase in fossil fuel and the human impact on our environments. So we play a role, an important role in this great acceleration. However, this great acceleration, and we come back to one of the first slides of this lesson, also concern the rising sea level rising trend, because also the sea level rising trend is accelerated since about the mid of the last century. And these are the two scenarios also in terms of relative sea level acceleration for the next century, more or less. Okay, so we have the best scenario and the worst scenario. With the best scenario, we have about 0.7 centimeter more of global sea level. Worst scenario is about 1 meter more of water sea level, global sea level. It's a lot. But also the best scenario is a lot of increase of global sea level, which could be the responses of alluvial coastal plains, delta plains to such kind of increase in global sea level. Why we think about coastal delta alluvial system firstly? Because they are flat, at low altitude, they are at the edge between the continental realm and the marine realm, so they are the first systems that will be damaged by such kind of sea level rise. In which way? It's not easy to obtain robust prediction of what will be, for example, the delta plain in the next century, for considering both best case and worst case scenarios. However, Antonioli and colleague a few years ago tried to map how much land will be lost considering these two scenarios along a different portion of the Italian coastline. And you can see here for what concerns the Po Delta plain, but also the Venice Lagoon, the Marano Grado Lagoon, that all this part in white will be submerged by 1 century. And obviously, we need more data to improve this kind of maps, because the authors cannot take into account the amount of sediments that Po River, this big river, the biggest in Italy, and the Apenninic River, Napine rivers can release at the coastline, and then in certain sense contrast to the relative sea level rise. So it's very complex. It's a very complex issue to reconstruct maps of this kind of map. But however, we can say that the geological record is the unique tangible record of expected future coastal scenarios. This is a crucial point, influencing the ability of different societal and environmental systems to mitigate or adapt to future change. In other words, we try to see how Po Delta, for example, and Po Coastal Plain reacted to past interglacial periods, to past similar increasing relative sea level trends, to better understand how this kind of system, the positional system, will react in the future. It's fine. So I think that's okay. It's the last slide. So perfect. Okay. See, yes, sure.
How can we distinguish between best and worst scenario if we cannot estimate the impact of human activities, for example, or policies? We are ignoring policies there, and we are just looking at let's say geo data, not human.
Yes. I don't know if I understand well the questions, but I can say that these two scenarios depending on how much will increase the global temperature. You have a range. The IPCC, the International Panel on Climate Change, defined two scenarios of increasing temperature for the next century. Best scenario, worst scenario, and transform this temperature, increasing temperature values into increasing global sea level rise. Fine. And these data are updated through time because you can add more data, you can obtain more nice calculation models, etc., etc. On the other side, the role of the geological record, this type of to answer to this question is try to reconstruct at the best as possible the paleogeography, let's say, of a specific area, for example, the Po Delta Coastal Plain, during the past period of time affected by similar sea level rising trend. Like, for example, interglacial periods. The last interglacial period, for example, was affected by an increase, a total increase of sea level of at least 5-7 meters more than the present day sea level. So it was a big interglacial period with a big rise in sea level. And we can check into geological record which kind of environment developed during such period of time in place of the Po Delta. Okay. And we see, for example, that during the last interglacial period, the Paleo coastline was more or less this one. So a big part, the remarkable part of the Delta coastal plain was submerged by the rising sea level of the last interglacial period, despite the high amount of sediment supplied by the Po River, the ancient Po River. So in this case, the sea level went against the sediment supply transported to the sea by the rivers. I don't know if I answered to your question.
So basically, every time we will see some sort of best scenario and worst scenario of the future phenomenon, usually it comes from the scenarios of temperatures and then they are translated.
For what concerns relative sea level, yes, the temperature is the main parameter that should be taken into account. Not the only one, it's very complicated. I think I'm not a specialist in this kind of calculation or modeling, but the temperature is the main parameters because we determine mostly the melting of the glaciers, the ice caps, essentially. I don't know if there are some questions also in the chat. I don't know if you have any questions. Also, if you have questions after the lesson, next days, feel free to send me an email if you want. Okay, no problem. And I hope that this is atypical, I think, for you. Data lessons will be useful for your program, your study, and maybe you can now look with a different eyes, some data, some information from the media. Okay, I hope so. I don't know. I think that if there are not questions in the chat, we can stop. I finished 10 minutes before, but I think that is good. That is fine. Okay. Well, I think that we can say bye-bye, ciao. Thank you to all for participating and have a nice evening. Bye.
Okay.
Ciao.